Question number 21. Worksheet forces on threaded rings. A block of mass 5 kg is held in equilibrium near a vertical wall by two light strings and a horizontal force of X Newton. Okay, 5 kg mass means 50 newtons weight in this direction, since weight equals mg and g is 10. Okay. Then it says two light strings. So these are two different strings. Keep that in mind. This is very important piece of information. So this string would have a different tension in it, and this string would have a different tension in it because these are two different strings. This is unlike the case of forces on a threaded ring where there's a ring here and there's a same thread or a same thread passing through it or a same string passing through it, and there's an isosceles triangle being formed, then we say that this is tension and this is the same tension. And usually it's mentioned that it's a smooth ring. Even if it's not a smooth ring and this is 60 and this is 60, then the tensions would be the same. But in this case, they're not the same because these are two different strings. Okay. Moving on, the two strings are both inclined at 60 degree. Given that x is equals to 100, find the tension in the lower string. Okay, clearly we cannot use Lemmy's theorem because there are four forces acting on the ring, acting on the weight. Okay, so what we can do is break the forces, the tensions into their horizontal and vertical component. There's going to be a component in this direction, and then there's going to be a component in this direction, which I'm going to draw parallel here instead. Okay, this one would be the sine component because it's opposite to the 60 degree. So this would be T2 sine 60. And the downward one would be the cos component because it's the adjacent between the 90 degree and the 60 degree. So this is T2 cos 60. Similarly, for the T1 force, there's going to be an upward component and a leftward component. The upward component I'm drawing here, and this component is the cos component, the sine component because it's opposite to the 60 degree angle. So this one would be T1 sine 60. And this one would be T1 cos 60. Okay, now since the system is in equilibrium, we're going to equate the up force, which is T1 cos 60, with the down force, which is 50, plus T2 cos 60. What is cos 60? Cos 60 is half. So we have half T1 is equals to 50 plus half T2. I really want to get rid of the decimal, so I'm going to do times 2 on both sides. So T1 is equals to 100 plus T2. Okay, let's call it equation 1. Okay, now I'm going to equate the left forces to the right forces. So we have two left forces, T1 sine 60 plus T2 sine 60. And we have one right force, which is 100. So this would be T1, what is sine 60? Under root 3 upon 2 plus under root 3 upon 2 T2 is equals to 100. Okay, this becomes under root 3 T1 plus under root 3 T2 is equals to 200. Okay. Okay. Next, what we can do is solve these two simultaneously and get the value of T1 and T2. I'm going to replace this T1 with 100 plus T2. So under root 3, 100 plus T2 plus under root 3 T2 is equals to 200. So we have 100 square root of 3 plus square root of 3 T2 plus another square root of 3 T2 is equals to 200. Okay, then this becomes, I'm sending the 100 square root of 3 to the other side, and these two combined become 2 square root of 3 T2, and now I'm going to divide the square root, sorry, the 2 square root of 3 to the other side, and this should give us the value of T2. I hope we needed T2. Find the tension in the lower string, yeah, which is T2. Okay, this would be 200 minus 100 square root of 3 upon 2 square root of 3. So 7.73. Let me check the answer. Yeah, 7.735. So T2 is coming out to be 7.735 rounded to 7.74 newtons, which is the tension in the lower part of the string. Okay, going back. Part B says find the least value of x for which the block remains in equilibrium in the position shown. Okay, so now x is x. So we're going to rewrite the equation. Up and down equation would obviously stay the same. So I'm rewriting this as T1 plus is equals to 100 plus T2. And this equation would change, and 100 would now become x. So I'm writing square root of 3T1 upon 2 plus square root of 3T under root 2, square root of 3 upon 2 T2 equals x. Okay. Now we need the least possible value of x. Okay, let's see. How do we get that? What we can do again is replace this T1 by this. So we get under root 3 upon 2, 100 plus T2 plus square root of 3 upon 2, T2 is equals to x. Okay, now this becomes square root of 3 and 2 and 100 multiply and we get 50. And then plus square root of 3 upon 2 T2 plus square root of 3 upon 2 T2 is equals to x. Okay, now we need the lowest possible value of x. Okay, when would this be the lowest? What should be the value of T2 so that this equation become lowest? It's clear that when T2 is equals to 0 for smallest value of x, which means when there's no tension 2, that means there's no lower string. There's only the upper string. Then this value of x will be equals to its lowest possible value, which is 50 under root 3. And in three significant figures, it would be 86.6.